Our presenter, Orri Jonsson, is no stranger to cold. He moved from the subarctic in Iceland to engage in work on cold atom experiments during his graduate studies at Colorado State University. After working with Gilliam cooling and epitaxial growth, Orri realized his passion lies in helping scientists achieve better results faster with better equipment. His journey brought him from precision optics to photovoltaics, cryogenics, and now back to laser-cooled atoms. Orri will now guide us through the chilly world of Cold Quanta's ultra-cold matter solutions.
Thank you for the kind introduction, Diane. I am pleased to see you all here. Since 2007, Cold Quanta has brought cold and ultra-cold science and technology out of the laboratory into the wider world to create a quantum atomics ecosystem. In support of our mission of democratization of quantum atomics, we've hosted a variety of webinars where we introduce attendees to techniques and opportunities in the world of atomic, molecular, and optical quantum science. I urge you to look at our catalog of webinars and see what you missed. Some of my favorites are Evan's introduction to laser cooling and trapping, Seth's introduction to ultra-cold matter, and Dana's introduction to quantum signal processing. The image here shows some of what we've planned for the future. The events page on our website serves as your portal to those and other educational materials about quantum atomics. Historically, we have had a two-pronged approach to democratizing quantum matter technologies, with the first being the performance of basic and advanced research on technologies and devices based on cold and ultra-cold matter. These include the development of Rydberg atom-based microwave sensors, atomic clocks, quantum memory, quantum key distribution, and quantum computing. For the second prong, we take the technologies and processes that we develop and turn them into hardware products, such as these here, that we provide to scientists globally and extra globally. This hardware and the research that scientists are doing with it will be the main body of today's webinar. Cold Quanta is excited to be launching a third way by which we're expanding access to quantum matter, and Hannah North will tell us more about this new brilliant development later in this presentation. She will take over from me in about 20 to 30 minutes, depending on my stress level. So let's start with Cold Quanta's simplest products. These are mechanically simplest, but the foundation of a lot of what we do. They are the glass cells. The cell there on the far right is the thin-walled, simplest of our cells. It's got a thin wall and no coating. Now, when we move to the middle cell here, we have the 2 by 2 centimeter square cell that has an anti-reflective coating on it, and also is much flatter, partially due to the thicker glass that gives you, so it doesn't bow as much under the vacuum pressure or the pressure of the lack of air on the back of it. This cell is polished. The glass for it is polished to exacting dimensions and flatness and scratch dig, and then coated on both sides, and then assembled using neither frits nor epoxies, which gives it excellent helium leakage rate, and also you can bake it to very high temperature. The cell here closest to me is the imaging cell, which has two sides that are extremely parallel and can be used with high numerical aperture imaging for experiments such as optical tweezing of atoms in the middle of the cell. So you can have high numerical aperture imaging of the cell right there. The standard glass cells I just show you are of course not always what people need. And so we create a lot of custom cells for people to meet their experimental goals. And so it's important for you to be sure what your goals are before getting in touch with us, or at least have a good idea, because the cell structure can vary a lot from, for example, from this triangle cell to the hexagon here. And so by bringing us in early, we can help you define the structure, and it can speed up the experimental process a lot. Now, of course, knowing what element you're working with and how you're going to do things tells us also which glass you're working with. Do we need to use, can we use Borofloat, which is our standard glass, or do you need to get into the ultraviolet, for which we need to use UV fused silica, which is a brand new product to us. And then, of course, there's the optical coatings that I mentioned before, which can be extremely important. Cold Quanta created a new paradigm in 2009 with the introduction of the Minimunt. It looks kind of big in the picture right here, but the physical device itself is the smallest atomic, is the smallest ultra-high vacuum system for a MUT that's commercially available. And it gives you, with a single power plug, you get a atom dispenser, an ion pump, and magnetic fields for trapping alkali atoms. It's available in cesium and rubidium versions. You can rest assured that you have the right optical configuration for your system when you bundle the Minimunt with the optics package. So here is a complete optics system for your Minimunt. Just plug in lasers and you are good to go. The Minimunt package is an excellent educational tool. Teachers in advanced laboratory classes just need to add lasers, and then you have a turnkey solutions for optics, laser, and ultra cold atom lessons. This workcourse can be introduced to introduce students to common techniques in atomic, molecular, and optical physics, and to do advanced experiments, such as 2-photon processes for quantum communication or for quantum memory experiments. Scientists have created optical traps, 2D optical traps, with an optical depth of up to 15 millimeters within this system. So there's some room for movement there. Now, when you go small, you often get the mechanical advantage of stability. And with the Minimunt and the Minimunt package, Dana Anderson took a Cirrus 22 aircraft from Boulder, Colorado to Cheyenne, Wyoming, while operating a magneto-optical trap in there. And this was the first demonstration of laser-cooled atoms aboard a general aviation aircraft. There's a video of that on YouTube if you want to see how that went and see the atoms live. But I mentioned two-dimensional traps earlier, and many ultra-cold atom experiments require a high flux of atoms while maintaining ultra-high vacuum in the science chamber. This is where a 2D MUT, 2D plus MUT comes in handy. At the core of the 2D plus magneto-optical trap or MUT is the cold atom source cell. This cell, shown here, this cell includes 2 atom dispensers, so you can have up to 2 species of atoms, say cesium and rubidium, provided to you from a single device. The 750 micron pinhole, you can just barely see there at the bottom, allows there to be a large pressure differential between this chamber here and your science cell, where so you can get a high flux of atoms just where you want them without having a high background gas pressure. Add some magnets, the Qcal optical system, and the appropriate lasers, and now you have a high flux of pre-cooled atoms. This is the Qcal that I'm holding right here, and for your experiments. The Qcal saves time and space with an alignment-free optical design. For experiments where the stability of the atom flux is paramount, the Qcal here can be ordered with an integrated laser beam monitoring. So we add photodiodes at the where the fibers come into the Qcal, and now you can compensate for any vibrations and such that may be causing atom flux variations. As seen on the charts here, with only a few milliwatts of laser power, you can in the regular picas, you can get atoms of more than 10 to the 9 atoms, or 8 times 10 to the 9 atoms out of your 2D plus MUT. But then with the active magnet picas, we have shown more than 10 to the 10 atoms out of the trap. This is a brand new development for us. This is the CASC2, or the cold atom source cell version 2, shown here with the permanent magnet stage. This cell has replaceable atom sources. So whereas the CASC1, when the atom sources were out, you had to buy a new CASC. And with this one, we can replace just the atom sources. So the total cost of ownership is lowered both with a lower initial price and with the option to just replace the atom sources and keep going. So the cell can continue to be an integral part of your experiment, even if after the original dispensers have been exhausted. Now that we have a compact atom source, so we have a small source of atoms for our experiment, we add an ion pump, we add some getters, and we add a science cell to end up with the double MUT. And the double MUT is a 2-chamber vacuum system, is one of the core products in our quantum core line of products. So here at the far end, we have the science cell. You can grab one here so that you see what the size that I'm talking about. So down here at the bottom, we have the source of the atoms that then go up to the science cell, where you do your exciting science. The science cell at the top there can be replaced with any of the custom cells that I mentioned earlier, or just upgraded cells. The base pressure in the science chamber is commonly in the 10 to the minus 10 range, and we achieve MUT lifetimes of up to 100 seconds in shallow optical traps. The double MUT is commonly used in ultra-cold atom experiments, where the lifetime of traps is of utmost importance. Now, we just created a new upgrade to the double MUT, which allows you even better vacuum. So we've doubled the lifetime. All right. I'll have to tell you more about that in person. Now, we can add a cell to the top, a custom cell to the top of the double MUT, but we can also add an atom chip. So the image here shows us an atom chip that has an optical window and some additional optical elements. The atom trap allows you to hold ultra-cold atoms a few microns away from a room temperature surface. That is an amazing temperature gradient that just always baffles me. So with the window there, you can not only hold the atoms and do any experiments that you can do with RF fields or large-scale lasers on them, but you can also project an arbitrary potential on there using, say, an acousto-optical modulator and a good imaging system. The smaller optics set around the window allow you to create a near-chip optical dipole trap or other fine-scale traps close to the chip surface there, so you get high transfer efficiency out of the magnetic trap into the optical trap. Here we have our friend Christina Koch on board the International Space Station installing the Cold Atom Laboratory. The Cold Atom Laboratory was first launched to the International Space Station in May of 2018. And last December, we launched, along with our partners at JPL, launched an upgraded science chamber to be able to do even more experiments there. They're doing 2 species atom interferometry in orbit. creating BECs and other ultra cold matter every day. And one of the things they're going to test is the equivalence principle by running these two atom species through the same processes in microgravity. A trap cloud of atoms is the foundation for a variety of ultra cold matter experiments, and the physics platform takes care of the optics needs for your experiment. Here, with the double mod and the physics platform, you have a ready-made optic system. Just add lasers, and you have ultra cold matter. Take that to an even smaller volume with the physics station. We've condensed it, brought in a couple extra levels to fit everything in, and when space is at a premium, that's where you want to go. Except when space is at a real premium, the channel cell is the future of ultra cold atom experiments in a portable package. This system right here is an ultra cold vacuum, is an ultra high vacuum system with a couple of Mott chambers and optics, so that you can run ultra high, ultra cold atom experiments in a tiny volume like this. This is a super exciting development. Now, all the equipment I've talked to hitherto has been for neutral atoms. So some of them may have been Rydberg atoms, but they've not let go of an electron. And at Cold Quanta here, we've entered the realm of compact ion trap systems with a pair of products. And so the compact and the cryogenic ion trap packages. There we can see the compact ion trap package compared in size to a standard ion trap package. The package is designed for an HOA trap or similar from Sandia National Lab, or a similar surface trap. And so if you have your own trap that you want to get a compact system around, it will likely fit in here. The vacuum has been shown to be in the 10 to the minus 12 range in there, so you will get good trap lifetimes at least. Vacuum is not going to be your issue. In a volume that's less than 3 cubic centimeters. Now, the cryogenic package shown here, just like the room temperature package, is made from titanium with C-cut sapphire windows that are anti-reflection coated. And the top window has a numerical aperture of 0.65 for high numerical aperture imaging of your ions. And then the other windows provide the laser access for loading the trap and have a numerical aperture of 0.12. Now, both traps have ablation targets for loading the trap, but there's a big difference in how we achieve the base level of vacuums. The cryogenic package shown here gets there mostly with cryogenic cooling, since it's meant to be used at 4 Kelvin or so. And so that helps you pump out most of the atoms, whereas the room temperature package has an ion pump, has an integrated ion pump. Now, let's go take a look. I apologize for that. In everything, my camera shut off over there. So I'm just going to move this camera here right now for the view of the complete ion trap system that we have, with the ion trap package here, an optical system that delivers all the optics, all the beams for trapping and ionizing, and then we've built this in collaboration with our friends at Toptica Photonics, Coherent Laser, and OptoSigma. Clinton will do a webinar on this here early in the next year. With our integrated laser systems, we provide the same level of integration or even higher level integration to our neutral atom friends as we do to our ion friends. This is this image here shows a 2U 19-inch rack that provides all the lasers for an ultra cold atom experiment for both pump and for both cooling and repump. We of course have created a line of electronics for all the needs of the AMO community. These include our atom chip driver, direct digital frequency synthesizer, coil drivers, and instrument control systems. Combined, these provide full experimental controls for the creation and manipulation of ultra cold matter. We are working on a PXIe version of these coming in the future, so even more integration. Here we have the Qcal ultra cold matter system. It's the first of a kind commercial turnkey ultra cold generation system. Gone are the days of giant optical setups and a spaghetti of cables to get you to ultra cold matter. The single rack here, about a refrigerator's mini refrigerator sized single rack Qcal allows the freedom to think about the intriguing parts of your experiment, while Colquenna's Qcal delivers the atoms you need. We are moving fast in the direction of providing customers with an optical projection system that mounts here to the top of the Qcal system. And using programmable modulation of the light, the system can create a variety of time-dependent and potentials onto the atom cloud through that optical chip that I showed you earlier. This is the first in our new line of commercially available turnkey quantum systems. And they are where we deliver a turnkey experiment. And there's a group of theorists at the University of Ghent that is getting the first one of these delivered. But what can you do if you don't have to wait for your experimental friends? Now, when I first started talking, I hinted that my esteemed colleague, Hannah North, would be telling us about some new developments. Hannah, can you tell us where you are standing right now and what you're introducing?
Hi, thank you, Orri. I'm going to go ahead and share my screen now, which will sort of spoil the surprise. But okay, I'm excited to share with you today that earlier this week, Colquenna has announced the early access program for Albert, our quantum matter system on the cloud. So that's where I am today. I'm amidst the quantum core and our laser table for this specific system. So as a part of the program for early access, we'll be accepting up to 100 users from North America and Europe. And in a moment, I will be giving you a preview of just how Albert is going to work. And if you are interested in becoming a part of our early access program, you can request an account online, and I will put that link in the Zoom. Okay, I'll put it in at the end. Sorry about that. Okay, so today I'll quickly walk through the soon-to-be-released Albert interface, and you can see just how easy it's going to be to start pioneering with Albert. Before I start, the experts at Colquenna and some members of this webinar today have constructed an awesome library of learning resources that Orri mentioned at the beginning of the webinar. And they can get anyone up to speed on ultra cold matter so that they can start to use our resources in their research, educational, or engineering projects. If you're new to cold atoms, or if we've piqued your interest today, our webinars are a great place to start with the basics. So regardless of your level of experience, you can really jump into experiential quantum learning using Albert coming soon. So the first step will be to create a free account on Albert. You can sign up to request the early access by the link that I'll provide at the end of this chat. And then as a free registered user, you will have access to all the tools that you need to create and explore with ultra cold matter. All right, so let's jump in. So the Albert Cloud interface puts you in control of the generation, manipulation, and imaging of ultra-cold matter. Users may create and submit jobs from anywhere within our early access boundaries, and Albert will automatically execute them in our lab in Boulder, Colorado, and deliver you the results in a matter of seconds. So you can begin your journey by creating a cloud of ultra-cold matter and imaging it, and we call this sort of process the ultra-cold matter generator. We'll refer to all of these processes as jobs just because that's the way that they're delineated in our web application. So for each job, you'll start with a cloud of cold atoms inside the quantum core in Boulder, Colorado. This object that you're looking at right here. Underneath all of these cameras and optics is a Rebecca system like Orri demonstrated before. So the initial cooling steps are automated and are executed by Albert at the beginning of the job. Once your atoms have reached approximately 300 microkelvin, then they will be transferred to a magnetic trap where you, the user, will take over the control of the experiment. And that starts with a cooling process known as RF evaporation. The easy click and drag interface that you can see on the screen here will allow you to try out different cooling profiles to achieve a different state of ultra-cold matter. You can experiment with RF cooling to try and achieve a Bose-Einstein condensate and rubidium, or you can optimize a cloud of different properties for your specific application. So when your job is complete, you can check out your results in the Jobs tab of our web app. This database of jobs will include all the results that you've generated with Albert, and you can continue to build your knowledge base all in one convenient location. It also means that you can review and continue to work with the results of your jobs when the system in Boulder is offline. Okay, so the technique for imaging ultra-cold matter that we're employing here is called time-of-flight imaging. Time-of-flight imaging characterizes your atom cloud by taking an image of the atoms held in a magnetic trap, briefly releasing the atoms and allowing them to move freely, and then taking a second image of the atoms. In the few milliseconds after you have dropped the atoms before you track them again, they fly in random directions with a velocity that's dictated by their kinetic energy. And this is the phenomena that allows us to learn about the atoms just by taking pictures. So the pair of images that you've collected will contain characteristics of your cloud, the number of atoms, and their temperature distribution. This information is automatically calculated by Albert. To learn more about the system that you've designed, you can change how long you let the atoms fly around before collecting a second image and start to put together a good picture of what your cloud looks like as it expands. Albert automatically does all of the camera calibration and image processing and just provides you with the important information that you need to know about each job. So on the screen here, you'll see a job results page with the time of flight data from a previous run. The thermal or high energy atoms, which have not been condensed into a Bose-Einstein condensate, have flown much further from their original position, which would have been the trapped position, and that indicates that they had a higher kinetic energy. The condensed atoms have an extremely low kinetic energy, and that means that they've stayed very close to their original trapped position in the time of flight interval. So in this specific instance, Albert has calculated that we've got 42,000 thermal atoms and 5,200 condensed atoms. You can see also an image here of the MOT, or the magneto-optical trap. That's the intermediate cooling stage before you proceed with RF cooling. So in lots of our products, you are making something that looks just like this, a MOT. So here's another run where you can see that we've created a totally different type of distribution. In this instance, we've got almost entirely thermal atoms. So they're still very cold, but almost none of them have condensed into that fifth state of matter, the Bose-Einstein condensate. So this was just achieved by altering the RF evaporation parameters. And those two totally different states of matter were generated maybe a minute away from each other. Okay, so now that you have supposedly generated some exciting new clouds of ultra-cold matter, you're ready to learn more. And you can do that with our barrier manipulator toolbox. This is your primary tool at the moment to interact with the quantum realm and conduct experiments using ultra-cold matter. Albert's barrier manipulator toolbox is a reconfigurable optical barrier capability, like Orri mentioned earlier. And you can use these optical barriers to poke, divide, and shuffle around ultra-cold atoms using light. This is achieved by shining a pattern of non-resonant light onto the trapped atoms through the atom chip, and this applies a tunable atom force to the cloud. This light pattern is generated using spatial light modulation techniques, so it's dynamically reconfigurable in time and frequency and intensity. So the barrier manipulator interface, like the ultra cold matter generator interface, is super easy to use, and it's all just click and drag for now at least. Quickly, you can reconfigure your potential in time, space, and intensity, and you can explore all sorts of exciting phenomena with unprecedented ease. So here we have some examples of ultra cold matter phenomena that you might expect to observe in Albert using the barrier manipulation toolbox. On the left is an interference pattern of two overlapping condensates. Interference is a quantum behavior, and in this image, we are observing the wave-like nature of these ultra-cold clouds. On the right is a Bose-Einstein condensate that was actually split into two separate condensates using tightly focused beams of light. This is very similar to those that are used in Albert's barrier manipulation toolset, and these are good examples of the types of moves that you can hope to incorporate into the choreography of your experiments. So this last example is a more complex circuit of ultra-cold atoms arranged into an atom analog of a transistor in an experimental system which we fondly think of as Albert's sibling over at CU Boulder. This is really just the beginning of a brand new and super exciting field of research based on circuits of ultra-cold atoms called atomtronics. So I hope that you have enjoyed this preview of the upcoming release of Albert, Quantum Matter on the Cloud, and that you will join us as we can explore the myriad applications of ultra-cold matter from the comfort and safety of our own homes. Sign up today to become a part of the first user group through the early access program, or just to receive updates on the launch and the progress of Albert. And so now, once again, I will attempt to put the link in Zoom.
Thank you, Hannah and Orri. That was great. We do have a couple of questions, Orri. So I don't know if we have you back yet.
I'm right here.
All right, there we go. Is the PICAS housing actually 3D printed?
Yes, yes. At the moment, the PICAS is in rapid development, and we are working on making it better and better. So 3D printing with a graphite impregnated thermoplastic is how the housing is.
Okay, and then this one I'm not quite sure. Is it a combination of cold atom and ion trap?
So I assume that the person asking is asking about the ion trap package, and it is not designed specifically for holding cold atoms, but just for trapped ions. So no, it's only an ion trap in there right now. To if you wanted to trap both atoms and ions in this volume, you would need to add some magnetic fields, and there might be some. It might be tricky to get all of the lasers in there for the cooling of the atoms. For the optical access that you need for cooling the atoms is greater than you need for trapping an ion, because with the ion you have an electric field to help you.
Okay. And Hannah, were you able to post that link in the chat window for early access?
I believe so. It's a form.
Yes. So yeah, if you click that link, you'll see a form too, and it just is asking a few questions. And we will be providing probably mid next week actual access to Albert. And I noticed in the chat window, someone asked about a link to the recording. We will be sending a link to all registered attendees, a recording of this webinar, and it is available on our website under events.
So I want to address the question that Evan answered live, because I think it's an excellent one, which is why do the experiments on the International Space Station and not what do we gain from being in microgravity? And so one part of experiments, when you're running these experiments on Earth, you grab the atoms, you hold on to them, and probe them. They can be in a magnetic trap, optical trap, or a combination thereof. And you hold on to them, and that affects the atoms. You're manipulating the atoms as you're doing your experiment in more ways than you maybe want to. Whereas, because as soon as you turn the trap off, the atoms fall down due to gravity. Now, going out into space, going into microgravity, you get a much longer time where the atoms can float around and do their thing before you image them. It goes from a few milliseconds, the time you have to let the system evolve without you interacting with it, goes from a couple of milliseconds or tens of milliseconds to seconds, which is an amazing, so you get 100 times more time to work with the atoms. And up in the space station, they have been able to get to temperatures in the picokelvin range versus the nanokelvin range on Earth. So yeah, there's a definite benefit to being up there.
So here's a question on how precisely can you control the number of atoms you put into the chamber? Can you go down all the way to a single atom?
Oh, no, you can't control it all the way down to a single atom, but you can create traps where you only trap a single atom. So you can put a few atoms into the chamber. You can make that quantity really small. But sending in a single atom is pushing it a little too far. But there are definitely traps, methods to send in atom just to where you need it, a small clump of atoms to just where you need them, and to capture one. Now with the 2D plus mod, you now have caught your atom that you're going to work with, and you don't have a background gas of other atoms that are going to collide with it and knock it out of the trap. You get this stream, catch one atom, and then do your experiment on it.
So I have another question, Orri, and I'm not sure, we may need one of our experts to chime in on this one. Oh, looks like that just disappeared. I guess they answered it, sorry.
Oh, no worries, no worries. It was about the Albert
yes.
Manipulation. Yeah, I saw that question. Let's see. So the question is, are there plans to allow additional optical addressing of the BEC and Albert with light closer to resonance than the trap light? And yes, as Seth said in his answer, we are looking for other techniques that people want on Albert. So we're starting with a free system with good capabilities for people to dip their toes into how to manipulate quantum matter for advanced labs in universities, and or even at the high school level, where people can see quantum effects on the macroscopic level. They can turn knobs that give them quantum effects and control a system. So that's where we're starting. But then once we understand better exactly what people are interested in, and we will add capabilities. You can think of it like a national lab particle accelerator or something like that, where there's a basic functionality that lives there, and then you bring in and you add in your own experimental tweak to it. You use the source that's already there, and now we just need to add what you want to do.
And what is the maximum time of flight Albert can achieve after release from the trap?
Oh, that's in the tens of milliseconds. I'm not sure exactly what the maximum is. I would have to call a friend and ask Seth to chime in on that if he has characterized, or Evan. Evan would actually know that. And Seth chimed in at roughly 40 milliseconds.
Great.
All
Okay,
right.
well, I think we've answered all the questions. And thank you very much to Hannah and to Orri for your presentation today. And thank you all for joining us.